turbine systems. So we're looking at quite a lot today. I'll just change my pen. Okay, first mammy, good. All right, so part 2. Let's see, get it going again. This is me again. Okay, content. We're looking at engine fuel systems, engine controls, supervisory engine control, authority, digital engine control, good old FADEC, lubrication system, so that's the oil systems, bearings that the oil systems will be lubricating, types of bearings, etc. Air sealing, we need to use air to help do sealing and in conjunction with the oil system. Engineer systems, again, a bit more cooling, how you can use air for various other bits and pieces. Drainage, things when we shut the engine down, where excess fuel and all that good stuff goes as well. Some accessory cooling, engine starting systems, various methods we'll look at how to start engines. Fire detection and protection. We've got a big hot engine in the back of the aircraft, so we need to do some protection, make sure, just in case there's a fire. And then the last thing will be the abbreviation or acronym list. A lot of abbreviations that mean quite a lot of the same things. You will become aware of these the more experienced you become in your industry. Again, as I say, we tend to speak in abbreviations instead of normal languages. All right, so let's start off. We're in the cockpit here. Again, just a generalized cockpit. This one we've got here is a twin engine aircraft. Okay, so there's a throttle on the left and a throttle lever on the right. So you go faster lever, you go slower lever, and we'll have what's below that. We'll have what's called an HPSOV, a high pressure shutoff valve, or more commonly known as a high pressure cock, which can be a separate one there. Okay, or it might be integrated with the actual throttle lever. Again, it depends on the type of aircraft. No problem. Along with that, we'll have an LPSOV. Now, again, these can be levers, they can be switches, which are normally left open. We'll cover these a bit later. But the three main ones are your HPSOV, your LPSOV, and your throttle lever. Now, the high pressure shutoff cock, that is the fuel for the actual engine itself, so it's primed, ready to go. Once you open that, you will supply fuel to the burner. The LP cock is the actual fuel from the aircraft to the engine. Okay, so the low pressure system, so that's where all your fuel from your wings, underwing tanks, main fuselage tanks, that sort of thing, and that's usually left open most of the time, unless for maintenance or emergency, which I'll come on to shortly. So it's the three main levers we'll look at the moment. Aircraft fuels, basically the fuel you're using is Jet A1, that's a sort of standard. There are a few other different names for it. We used to call it F-34 when I was in the military, but pretty much the same thing. And it's a heavy fuel, it's like a diesel, it's a kerosene, and generally used in turbojets, turboprop aircraft, and most commercially known as Jet A1. So the fuel system requirements, turbine fuel should have the following qualities. Now this is a word, it must be pumpable. In other words, it should be, the fuel pump should be able to make it flow easily under all operating conditions. It doesn't matter what the aircraft's doing, as long as it's flying correctly in the correct envelope, it should be able to, like late arrivers, it should be able to operate under all conditions. Yeah, but it's high level, low level, fast, slow, whatever that aircraft, that engine designed to do, that fuel should be there ready to go. Okay. It must permit engine starting at all ground conditions and also give satisfactory relighting characteristics. Now, relighting, when the aircraft's flying, it might fly through some adverse weather, really bad weather up in the altitude, potentially have a flame out. Now, depending on, even though it's at height, it should be able to relight under normal starting conditions. But again, that's down to the pilot as well. But basically, the fuel, it should work what it's designed to do. It should give efficient combustion, under all conditions, not just go and fire sometimes, but it should go and fire all the time for all conditions. Another one is it should have as high a calorific value as possible, lots of energy. You look at some of your drinks you might drink, high energy drinks. They've got a high calorific value. The higher the calorific value, the more energy in that substance. Should produce minimum corrosive effects on the combustion system or the turbine blades as well. Unfortunately, though, the fuel is corrosive if it stays still. Yes, it's designed to burn, so it's going to be quite volatile. So if you just leave that sitting about, it can be quite corrosive. But again, as you set fire to it, it should do its job and not be too detrimental to various components as well. Okay. To produce minimal corrosive effects on the fuel system components. So yeah, within the fuel system itself, it shouldn't be degrading fuel systems, breaking down components or damaging seals. It's okay when it's moving. When it stays still for a while, then it does through time, it can be corrosive. And we have to do what's called an inhibiting process, which again, we'll cover later on. It should provide adequate lubrication for the moving parts in the fuel system. So yeah, you've got the fuel pumps, you've got the seals within all the components, various bits and bobs that will be moving within the fuel system. So as well as being there for combustion, it also helps lubricate as well. But if we want to reduce fire risk to a minimum, well, it's a fuel, it needs to go on fire. But what we mean by that is that if it's not in the combustion system, then it should be as safe to handle as possible. Now, because we work on gas turbine aircraft, the fuel, as I said yesterday, if you put a lot of that gas turbine fuel or jet fuel in a bucket, put it in like a cold day here, put a match in it, it won't go on fire. But in a very, very, very hot day where it's maybe evaporating, then yes, it becomes more volatile, more dangerous. Normal petrol, like for motorbikes and your cars, that's a high risk fuel. It goes on fire very, very quickly. Again, we'll cover that shortly. But when it's not being in use, it should be as safe to handle as possible. But at the end of the day, it is designed to go on fire. Satisfactory ignition and relighting of the fuel depends upon two factors. I've just mentioned briefly there, the volatility of the fuel. In other words, its ability to ignite under certain conditions. Okay, change from a liquid state into a gaseous state easily, and especially at low temperatures. So the jet fuel compared to like a normal petrol is less volatile, where the petrol is a high volatility. It doesn't need much of a temperature, doesn't need much of a pressure to ignite, whereas your Jet A1 does need a higher temperature and a higher pressure. Now, the degree of atomization, again, which will depend on the viscosity of the fuel pressure, and the design of the nozzle. So we looked at the burners yesterday, the different types of atomizers and even the vaporizer. Okay, so again, viscosity is resistance to flow, so the ability of that fuel to flow, and the thicker it is, the harder it is to ignite, so it has to be designed specifically for that system and be able to go through all the components. So a few properties of Jet A1. The flash point is only 38 degrees C. So if you had a hot day, some countries can be above 30 degrees. Okay, then it's starting to evaporate. You know, it's getting to the point it will ignite very quickly. Here in Scotland, it's probably, if you look, it's about 8 degrees. So there's not much chance of igniting very easily. Specific gravity is about 0.81. We usually call it 0.8 at standard sea level temperature conditions at 15 degrees C. That means it's lighter than water. If it was 1, it'd be the same density as water. Remember, we used to use in module 2 for specific density of a substance was over 1,000, and water would be the most dense as a reference point. So specific gravity is about 80% the density of water there. And most fuels are roughly about 0.8, 0.78, or maybe 0.82 thereabouts. Okay, so it is quite a dense one, but not quite as dense as water. So things like if you're doing your water sediment checks, we take a tapping water fuel from your wings or a collector box, and you let it settle. If there's any water in there, the fuel will sit on top of the water, so that every time you do your water sediment checks. Using temperature of the fuel, yeah, it's quite low, minus 47 degrees C. So if you're in a country that's that cold, well, good luck. It's not quite that cold in Scotland, but certainly places like Alaska, Canada, and that sort of places, it can get extremely cold. But at least the fuel will not freeze up till it's about -46. It will start to get thicker, the viscosity will increase, and we'll actually get to a point where it will crystallise. But we've got some additives we can put in there to help the fuel, which we'll cover. So yeah, there's a picture as it gets very cold. It starts to get sort of crystallised. Okay. Again, you have to be watch out for that in very extreme cold conditions. However, we tend not to start aircraft below -40. That's pretty much the cut-off. About -40 degrees is probably where we will stop trying to start an engine. It's -40 degrees. That's far too cold to be outside for a start. Yeah, never mind flying an aircraft. Now, what we call kerosene is hygroscopic. That should be hygroscopic, which means that it will attract and absorb moisture from the atmosphere. So even if you expose the fuel to air, it will absorb the moisture from the air as well, which is again not too good. Okay, what's better? I'm going to try and find there for you. It's okay, I'll come back to that one. Okay. Volatility, briefly mentioned there. Again, the ability of it to go on fire. Okay, so it means the degree at ease at which a liquid will change into a vapour. The greater volatility, the lower the ambient temperature required to convert into a gas. So like your normal petrol for your bike and car, it doesn't need to be a very high temperature. It will self-evaporate even at low temperatures. It will go on fire rapidly. We do have different types of fuel called avgas, which is aviation gasoline, which is pretty much the same as motor car, just a bit more volatile. Again, which some piston engine aircraft can use as well. The lower the ambient pressure on the liquid, the lower the temperature at which it will boil. In other words, it'll turn to vapour as well. Now, in your books, we don't mention the pressures, just a bit of background information, but we've got a thing called RVP, read vapor pressure. And this is the common measure of the volatility of a gasoline. And for typical gasoline, only about 2 to 3 psi, which is about, as I'm breathing out now, do that, it's about 2 to 3 psi at standard sea level temperature conditions at 15 degrees C. Okay, it's a standard read vapor pressure, basically the volatility of the gasoline. Most important that you use the correct type and grade of fuel should be used as indicated in your maintenance manual. 9 times out of 10, it's going to be Jet A1. There are other fuels you can use depending on conditions, but you have to be aware if you put the wrong fuel in, there's a chance the engine might not work correctly. Again, that'd be like putting diesel in a petrol car and petrol in a diesel car. It will sort of work for a bit, but not very well. So we've got some other types of aircraft fuels. First one is a Jet A. Again, it's a kerosene or a heavy diesel, heavy paraffin type fuel, and that has a freezing point of around -40. So the Jet A1 was -47. This one's quite close, around about -40. It's only available in the good old America. Specific gravity range of almost similar sort of standard, 0.775 to about 0.83. So it's about roughly the same. So you could almost use that one if you're really stuck. Jet B, this is classed as what's called a wide range distillate, known as a wide cut gasoline. Not in common use. Tends to have an SG range of around 0.76. Okay, so even lighter than Jet A1. Tends to be more military aircraft for that one. Jet 4, again, another wide range one known as a wide cut gasoline. Certain additives are present, and it's known as AVTAG or aviation gasoline, again for military use. Anything that's got AVTAG or AVGAS or AV beside it, that usually means military use. Specific range, again, it's a bit lighter, about 0.76. And we've got JP5, I should say. Again, a high flash point kerosene, mainly for aircraft carrier use. So again, military use, may also be known as AVCAT. Again, specific gravity range of roughly similar of Jet A1, 0.83, so it's a bit heavier. But again, the most common one you might come across, if you can't use Jet A1, is probably Jet A. That's probably as close as you'll get to using something completely Jet A1. Okay. Avgas, again, that tends to be for piston aircraft. It's pretty much the same as your piston aircraft, piston engines, your cars and motorbikes, but it's a lot more volatile. Okay, you're getting more to the Formula One type stuff. Okay, so it will have a low flash point. It's got a low lead content as well. There's another thing called MOGAS. If you do module 16, it's basically the standard petrol that you can actually land a piston aircraft. If you don't have petrol on a piston aircraft, you can land, go and fill up a normal petrol station, put it in, and you can fly your piston aircraft up to about 6,000 feet. So by putting standard petrol in a normal piston aircraft, you can use that if required. But again, for us, for gas turbines, Jet A1 is the normal fuel you will use. And you'll see that in the tanker. So if you see a refuel tanker come out to your aircraft and it doesn't have Jet A1 on the side, then certainly go and ask what fuel he does have on the side. You don't want to put the wrong fuel in your aircraft, especially if it's a big aircraft, because it takes a long time to defuel. Solid fuel is great, but again, safety precautions is paramount. As well as spilling and fire hazards, look after your health. Fuel will degrease your skin. You'll get things like dermatitis. If you have cuts in your skin, it can cause a lot of skin problems. So make sure you're using barrier creams. Wash if you get any fuel spilt on you. Wash it off as soon as possible, and you know, especially when you're working on components, you could be underneath an engine. You take a pipe off, you get covered in fuel. Go and get cleaned up straight away. It does have a lot of detrimental effect. As you see, for me, I've lost all my hair. Yeah, it does burn when it's hot. It does burn and sting. If it gets in your eyes, get the wash bottles out. Okay, and seek medical attention if you do get covered on it. If your protective clothes get soaked in the fuel, don't just wash them, just bin them. Okay, your overalls that you might be using, if you do get, you may be taking a pipe off and get covered head to toe. I've seen it happen a few times. Once you wash those overalls out, you're actually losing the fire deterrent that's in those PPE overalls. And the best thing to do is just bin them. Okay, you become a walking firebomb in effect, where it's very easy to go and fire. So go and get a fresh pair of overalls from stores and make sure you keep safe. And so say degreasing properties of fuel. So if you don't protect it, you can end up with skin problems. We don't want that. Aviation fuels are also carcinogenic. I need to change the spelling that. Sorry, make a note of that one. Forgot about that one. Carcinogenic. In other words, it causes cancer. Change that one, get right. So yeah, everybody has cancer in the system. It takes something to activate it, and aviation fuels can be the trigger to activate it. So again, don't stand behind the exhaust breathing it all in. Any smokers there? Don't smoke. Again, that can cause cancer. We don't want cancer. Bad enough with everything else in the world. So I mentioned earlier, we can put additives in the fuel to help the fuel. It is dangerous stuff at the end of the day. It does need a little bit of help, though. It's very volatile. It's designed to burn. Again, extreme conditions can cause some problems. So we're going to look at some of the problems and some additives that we can add in there to help the fuel do its job. Now, electrical conductivity. We need a static dissipator. Now, why on earth would you need something to do with electrical in the fuel system? A static dissipator. What do you think that could be? Anybody?
Same as a grounding? Yeah.
If you look in your houses or even in the buildings there where you've got a sink, anything with taps, even for the water, if you look underneath the taps, underneath the cupboards, there should be some sort of grounding or earthing leads, the green and white ones attached to your pipes. Any moving fluid will cause friction. What does friction cause? Static electricity. Now, in water pipes, that's not bad. If you get a bit of static, you touch a pipe, oh, you get a little, maybe a little tingle if it's not earthed properly. Static in a fuel system, well, that can be very dangerous. We can get sparks at the wrong time, the wrong place. We want sparks in the combustion chamber, and that's it. We don't want sparks anywhere else. So the fact that fuel is moving through pipes, that can cause static buildup. Now, all your pipes work, everything on aircraft is grounded, but to help prevent that static buildup, we can put a static dissipator in there. Okay, and that just helps sort of dilute the actual chances of getting static buildup. A corrosion inhibitor. We think, well, yeah, fuel is volatile. It is corrosive if it's not moving. So we put in there to help lubrication. Okay, so it helps it move freer and stops attacking the metal and the pipeworks breaking down various components. So we can put a corrosion inhibitor there as well. And we can sometimes add what's called strontium tablets. They look like a little pack of sweeties. Now, these are optional. So every fuel you get to use in aircraft will have all these things already in it. Sometimes we can add these little tablets into the tanks as well. When we got taught back in my day, we got shown them. I've never ever used them on aircraft. Usually the fuel is ready to go. This will be more done at specialists, back at the fuel dumps and that sort of thing. But again, I have seen it, going back to cars and motorbikes though, saying that, we have seen these tablets you can put in your motorbike tank, because through time, you always have water and fuel. You never get rid of water and fuel. Every time you open your cap on a fuel tank, air gets in when you fill it up. So through time, the small amount of water that's in there will start corroding your fuel tanks, especially motorbikes, sits at the bottom, and sometimes eventually they'll start leaking at the bottom. So we can add these strontium tablets, which help prevent corrosion as well. But essentially what you should have though is FSII, Fuel System Icing Inhibitor. Even out in Nepal, you'll have this in your fuel tanks already. It also acts as a lubricant, but the main thing it does, it reduces the freezing point, not of the fuel, but of the water, because obviously water will freeze quicker than fuel. As we saw earlier, the Jet A1 freezes about -47. We can do engine starts about -40, that's fine. But remember, we've always got water in the fuel. You'll never get 100% water out. So if the water freezes in the fuel, that can cause a lot of crystals, which can cause a lot of problems, clogging the fuel up. So by adding FSII, we can actually reduce the freezing point of water down to, as it says there, about -47 to about -50. So more in line with the freezing point of the fuel itself. Okay, so FSI reduces the freezing point of water, not the freezing point of the fuel. Okay, and that should always be in the fuel. It's pretty much standard now. You'll see the Bowser as your fuel for refueling the aircraft come out. You'll see Jet A1 on it, and there should be a symbol on the back of the Bowser or on the side saying FSII. So it acts as a coolant and for hot days and hot climates, but also as an antifreeze for the water as well. So it does a few things there. Biocides, unfortunately, if you've got water in fuel, then water is the creation of life, isn't it? So if you've got a hot climate, and certainly when we get to above 25, 26 degrees, any water in there has potential as bacteria. Bacteria like warmer climates. So they're not much use out here in Scotland, but always quite cold. But certainly in Nepal, when it gets hot and above 25 degrees, the bacteria will go, oh, we're on holiday now. We can start multiplying, that sort of thing. It becomes like a fungus. It's a really smelly type substance if it gets hold, and we don't want that in there. So we can put biocides to help prevent that. And the biocide that we speak about is a nickname we call Gladys, and that's short for Gladys sporin resinae. Okay, it's if you've ever had a tank of fuel, it's maybe been sat for a long time. I mean a long time. A drum of fuel, it's been left at elements. You open it up, and old fuel stinks, doesn't it? It really smells terrible. If you leave it really long, you'll end up getting the fungus will build up, and it's just a big smelly. Oh, it's not nice. Okay, so it's a culture clad. The top red is portion of fuel. We've got in this diagram here. The lower section is water, because obviously that's thicker than the fixture. Then in between that, you've got the actual fungus, this gloopy, smelly, stinky stuff. Okay, and that's settled suspended in the fungi. If you find that in your fuel system, you probably have to go into drain all your fuel system, clean it out, flush your pipes, potentially take some components off and clean it all out first. If your fuel system in an aircraft gets that bad, it's often been sat for a long time. Okay, so hence why we call what we do in the inhibit, we actually get rid of fuel if an aircraft's going to sit for a long time. And yeah, that could be sitting in your fuel tank. And I have seen fuel tanks, not on aircraft, but certainly on farms. Around here, we had to, when I was a younger person, I used to work in a garage. We cleaned out some old fuel tanks for tractors. And again, they've been open maybe for too long, and it was stuff like this, and it's absolutely disgusting. It's not nice at all. If you see that, it just spreads. It spreads quite quickly. But it only likes certain conditions. It likes to be in a hot climate. So you're looking about plus 25 degrees. Anything below that, it will always be in the water, but it'll sit dormant. Once it gets hotter, it goes, I'm awake now. You know, then it'll start doing its job. Hygroscopic ability, again, we mentioned that, ability to retain moisture, or water in this case. And as always, if you're doing water sediment checks, taking samples of fuel to check if there's any water in there. Again, water is always heavier, so it will sit at the bottom. So ideally, what you want to see if you do a test, you want to see this, just fuel only. There will always be tiny particles of water in there. You never get 100%. But again, you might have air bubbles, you might have sediment, and you know, this sort of thing. At the end of the day, you want to see a nice, clean tube. Now, when you go to refuel your aircraft, when the Bowser driver comes up to refuel the aircraft, you should always ask them, have you carried out your water sediment checks? And if the Bowser driver says, oh, no, I've not, well, don't put any fuel in the aircraft until he goes and does the Bowser checks, because if he has refilled his Bowser, the truck, and potentially got lots of water in it, then you're going to put it in your aircraft, that can cause a lot of problems. So always ask them, just politely say, have you done your Bowser checks? And you should say yes. He might be lying to you, hopefully not. And then off you go. Some aircraft I used to work in, part of the daily services was to go and take a sampling from the wing box, drain it off, and then check there's no water. If we found water in it, we would keep draining until there was no water available. Normally, you maybe get a cupful. It was never too much. Sometimes, if somebody hadn't done it for a while, yes, there'd be a lot of water. But you do it as many times until you're seasick. If there's lots and lots of water, well, that's obviously a cause for concern, and you might have to defuel the aircraft and go and do some checks on it. Okay. Cleanliness is godliness, isn't it? Look after your tools, look after the equipment. Anytime you go and work on aircraft, you should be nice and clean. Yes, you might get dirty at some points, fuel comes out, oil comes out, but make sure when you're working around fuel components, you're in a clean environment where possible. Don't work in a dusty environment. I know in Nepal, it can be quite dusty sometimes. So again, most of the time, try and work on your aircraft in a hangar. Don't leave anything open. If you disconnect a pipe, always make sure you put blanks on the components like we've got there, and the correct blanks as well. We don't want any FOD or foreign matter going into the pipes, even the smallest particle. If that gets in a fuel system, that can potentially block burners and other parts. Any sort of contaminants, in other words, anything that should be in there, it should be in there. You might be put some grease on a control rod, you might have some in your hand, you go and touch a fuel component. Make sure you just keep things clean. So disconnection points, I said, if you disconnect a pipe for some reason, don't just leave it blank, open to the elements, put a blank on it if you're going to leave it for a while. If you're working on it straight away, that's not so bad. But again, just be very careful. Blanking, specially designed ones, don't put inappropriate ones. Don't put anything with paper or cloth in there, because paper or cardboard, that can potentially go into the pipe, and then we connect it back up, you don't see it, and off it goes and blocks your fuel system. Suitable material. Typical blanks that we've got in here, all designed specifically to fit on the component. And most of the time they're red to let you know there's a blank fitted. Reconnection. Yeah, well, you've got to remove the blanks. But again, when you're removing these blanks, some of them can be quite small. Make sure you put them in a bag or an appropriate box so you don't leave them lying about. Again, because they could become a FOD article and can be sucked up in the engine when the engine starts up. Jointing compounds. Yeah, sometimes you might have to put some sealant around parts, some connections. Only put as much on as you require. Don't put lots on there, because when you join the pipes together or the component, some will squeeze out outside. That's fine, you can remove that. But some will also squeeze inside the pipe. Now you won't see that, and what will happen, that will go to the fuel system, it will solidify, and again, that becomes a hazard for the fuel system, potentially blocking components. Okay, so joint compound, you can see there, put in the good old Hylamar. Only put small amounts on as required. Use what's called a stipple effect. Some people just put it on like a bead like that, but put a thin layer on and actually just stipple it. Sometimes use a brush or your finger on using protection, and that'll give a nice good join. But only put as much as required on. Don't put loads and loads on there. Okay. All gas turbine engine fuel systems have to do this. They must provide a continuous supply of fuel. Makes sense, yeah? We don't want it intermittent. Be correctly atomized for combustion. Provide a fuel flow relative to the selected position of the cockpit by the pilot or yourself as an engineer, and thus therefore allow manual selection of the RPM of the engine. Correct fuel flow for changes in ambient or intake conditions. So forward speed, that's going to change ram effect, altitude, temperature coming back down from altitude, pressure and all that good stuff. Prevent excessive over or under fueling. So when you move the throttle, you want the fuel to respond as quick as possible, but at the same point, you don't want to overfuel, and likewise, you don't want to underfuel. So if you move the throttle forward and it underfuels, then that's not any good either. And likewise, we don't want too much. We want the fuel to be there at the correct time and correct speed and the correct pressure, etc., or whatever the selection is. Ensure that the maximum limits for engine operation are not exceeded. Okay, so a fuel system, as well as providing the fuel, we've got to control it. And we're going to look at all the methods today of, well, certainly the basic methods of how we control that fuel as it goes to the combustion chamber. So back to the first slide, we mentioned 3 levers, your HPSOV, your LPSOV, and the throttle lever. So we'll look at the low pressure one first. This is where we get the fuel from the aircraft itself, and then through a valve goes towards your engine. Now the purpose of the low pressure system is to isolate the engine system from the aircraft system in the event of an emergency or for maintenance procedure. Now it might be worth highlighting that in a book. If I don't, it's in the book you've got at the moment, but certainly make a note that this valve here, we call it an LP cock, when you move the LP lever, it will open or close this valve here. It's just a ball valve, just a round ball that has a hole through the middle that will rotate 90 degrees, will be closed or open. Simple as that. It can be a manual lever on the top connected to a rod, or it might have a solenoid, electrical actuator. Okay, and these electrical actuators also have an indication, so it can physically tell you what position it is. You can put your hand on it or the direction on it. You can tell if the valve is open or closed. Now, normal day to day, this will be left in the open position, and the switch or lever is usually guarded. Certainly some aircraft I used to work on, a big red gate would cover the lever to make sure it's on. So if you want to switch it off, you'd have to open the gate and then physically switch the lever to off. And it's normally just for emergency and for maintenance procedures. Now, for maintenance procedures, it's because if you've got a big, huge aircraft and you're going to remove an engine, well, rather than defuel the whole aircraft, just take an engine out, we can switch the LP cock off. That isolates the fuel from the aircraft side, so you can now disconnect your engine without having to defuel all that fuel in the aircraft. So nice and simple. So emergency, yeah, you've got a fire, we want to shut down the engine rather rapidly, we don't want any more fuel going to the engine, we can shut the engine down, switch the LP cock off, and that won't supply any more fuel to the engine, and hopefully you can deal with the fire as well. The firemen are trained to carry out emergency shutdown procedures on certain aircraft, and especially when I worked in the military, we have 2 people in the cockpit normally. So let's say the pilot was incapacitated for whatever reason, the fireman can come up and he would know how to switch the fuel off, and that would be one of the very first switches. Let's not supply any more fuel to the fire, LP cock off, and all good. Now, one thing to be very careful of is make sure when you refit an engine or you have isolated for maintenance purpose, you switch that back on, because if you go to start an engine with that valve switched off, you'll end up what's called cavitating the fuel pipes. In other words, the engine will be trying to suck the fuel, but there's no fuel there because this valve is shut, and it will just, you imagine it sucking a straw, it will collapse. Okay, so actually what's called cavitating the pipes. That gives you a lot of work to do. So be very careful. Yes, isolate for maintenance, but make sure as you're restoring procedures, ready to do a ground run, etc., that you make sure it's switched on. You'll do that. Part of your pre-flight checks and also pre-start checks is to ensure that is switched on. But it can be missed. It has been done, believe me. So I said there, the type is normally a ball valve, mechanically or electrically operated through 90 degrees, as mentioned already. And operation, again, rotated from fully closed to full flow position and vice versa. Mechanically or electrically, and we'll have mechanical stops, so 90 degrees open or closed, as well as limit switches if electrically actuated. In other words, limit switches will give an indication of cockpit that it's closed, and once it's open, usually the light goes off. Now, things that can go wrong with these is a mechanical valve, they can stick through time. Now, you might have an electrically operated one, you switch it to close, and you hear the solenoid go zzz like that, it shuts, but actually what's happened is the shaft might have sheared. So the solenoid has moved, and for all by accounts, it's telling you it's shut, but the valve hasn't moved. So when you go to disconnect your engine and you disconnect your LP fuel pipe from the valve to your engine, you have all this fuel coming out, and you've got to be very quick to try and stop all that fuel, thousands of gallons of fuel coming out of your aircraft. Usually, though, on your fuel pipe from the engine, from the aircraft to the engine, there's usually a drain connection, a little small drain blank. You can disconnect that, and you might get maybe one or two buckets of fuel coming out, and that's usually as much you'll get. Basically, how much fuel is in the engine itself. If you're going through buckets and buckets and buckets, you've probably got a faulty valve. Okay, so after about 2, 3, 4 buckets, I'd be checking that your fuel valve has physically shut off. If it's faulty, the only way to change it, unless there's another valve behind that, which there usually isn't, is drain the aircraft. That's to defuel the aircraft. Replace the valve, make sure it's working, and then you can refuel the aircraft again. So just be careful of that. That's just the basic diagram you've got in your book. Of an overlay of the type of fuel system you might have. So from front to back, we've got HP fuel pumps, we've got governors, we've got throttle box, HP shut-off cock, fuel control units, propeller control units, and a turboprop, and the same sort of thing again for a turbojet. Okay, again, just a general oversight of what the things we're going to be actually looking at. Okay, just a general oversight. Okay, right, let's just double check there. Got that one. Oh, no, that one. Yeah, on the one I didn't have in the book, in the PowerPoint, I did mention the temperatures. Going back to the bacteria, the glassiform resinae, if you want to make a note that the temperature is usually between 25 and 35 degrees, so quite a warm environment. If you want to write that down somewhere beside the glassiform resinae, 25 to 35 degrees. Just make sure, so I've got a new book here. That's okay. Yeah, okay, that's the only one I want to just double check on there for you. All right. So we'll start looking at some of the components involved in the fuel system. I'll start a couple and then go for a break. Okay, so one of the components to look at is what's called an FCOC, a fuel cooled oil cooler. It's a body-body system. Now, obviously, there's a section cutaway of it. It's basically a radiator. Think of a radiator. Again, I keep using cars and motorbikes, but trying to make it as realistic as possible. A radiator in your car. You have the very, very thin matrix, okay, very thin veins, that the air from outside flows through. In those veins is your water, your coolant for your engine. Now, the air cools the water, but the water can also warm the air within the engine bay. It helps keep the engine at a reasonable temperature. But we don't want the water or the coolant going too hot. An FCOC does the same sort of thing, but this time it's fuel and oil. Okay. Now what we've got, if you cut inside, it's hard to see in here, but these little tiny dots are little steel rods, lots and lots of little steel rods. Okay, from front to back. Now, what flows through the rods, or these matrix as it's called, is the fuel. Okay, so fuel comes in from your wings, your fuselage, wherever. That flows through these little rods, little matrices, and in between the rods is your oil system, flows all around it. So the cold fuel helps keep the oil cool, and then once the engine gets warm, the warm oil warms the fuel before it goes to the combustion system. So it helps preheat the fuel a little bit. Without either or, you'll end up one system getting too hot, like the fuel getting too hot or the oil getting too hot, and that sort of thing. So the cool fuel from the wings, etc., flows through this cooler. So hence why it's called a fuel-cooled oil cooler. But it is a body systems, I call. Okay, now don't worry about the IDG and stuff at the moment. It's just an example of one. But what we would have is we will have obviously seals to prevent the oil going to the fuel and the fuel going to the oil. The tubes are called, as I said, they're called a matrix. We will have what's called baffle plates because the oil will be moving about in there. Now, if oil is moving back and forward, that can cause a lot of potential problems. So the baffle plates just slow it down. It keeps the oil within there, but not moving about or sloshing about too much. We'll have fuel going on one side, going through the matrix, and then going through back to where it's going to the outlet. Oil will come in one point and go around all the matrix, and then eventually come back out to the bearings, etc., back to the oil system. Attached to the cooler, you will have an oil temperature transmitter. And that will tell us if the oil temperature is getting too hot. And we'll cover that a bit later on. Also in there, you'll have an oil bypass valve. Now, the reason we've got an oil bypass valve, when the engine's very cold, especially in a very cold environment, say like a Canada or Alaska, or even here in Scotland, the oil will be too thick. It'll be quite viscous, very high viscosity. Okay, so it's going to be very thick. So trying to move oil through all these thin tubes will take a bit of time. So thick oil will cause a bit of pressure. The pressure will push against this valve, open the valve, and allow the oil to go to the bearings as normal. And once the engine warms up, the oil will become less viscous and become thinner. Then it can flow all around the actual cooler itself and then go back to normal. Okay, but initially, if the oil's too thick, it will move this valve and everything will be happy. Okay, so that's a basic of an FCOC. You do get different versions of these. You get what's called an ACOC. Does the same job, but it's an air-cooled oil cooler, more like your radiator in your car. It'll be air cooling the oil, okay? Same sort of thing. So that's an FCOC, fuel heater and fuel cooled oil cooler. LP fuel filter, so low pressure filter. Yeah, first line of defence. So you've got the fuel in your wings, your fuselage, underwing tanks, etc. Well, as it comes through from the fuselage, etc., we need a first line defence. We need the initial filter. And it's quite a coarse filter, usually made from paper or felt. There are different versions now. And these are what get serviced on a regular basis. They will also prevent large particles of debris potentially in the system. Obviously, in your fuel system, it should be clean, but seals degrade, little bits of metal might come off, pipework or tanks or bits of rubber and that sort of thing. So this filter will help block some of that as well. Again, depending on the type, you'll have some sort of a nut to take it off or a retaining lock. Always change the seal. Even the seal looks okay. When you take it off, cut it, throw it in the bin, get a brand new seal. Never put an old seal back on. And that goes for any component. Even if it looks okay, you must put a new seal on. You don't know how long that seal's been in there. Okay, so that's the filter element. Now, in the filter housing, there might also be attached to it a differential pressure switch. Now, that's there to let you know that should this filter get blocked, well, if the filter's blocked, it won't allow any fuel to your engine. So by having a differential pressure switch, it will have a predetermined pressure. And if that gets activated, that will put an alarm or warning in the cockpit to tell the pilot and yourselves that the fuel system is about to become blocked. Not blocked, but about to become blocked. There's no point in telling you when it is blocked because that's too late. You'll soon know because your engine will shut down, especially if it's blocked. Okay, so there's not usually a bypass as such, because that can cause a lot more problems, to be honest. Okay, so that's a basic LP or low pressure fuel filter. Then we've got various flow transmitters. We'll look at some different ones again later on, but a basic one we've got there is this one's called a variable orifice one. It looks like a rudder on a boat. Okay. Now, as the fuel comes in here, the faster it's moving, the more flow, the more pressure it'll put on here. And it will try to move this gate, this measuring vane. Looks like a rudder off a boat. Now, the gap that is at the end here against the casing does get larger the more it goes around. It's not the same distance all the way around, but it does get larger. It's calibrated. It is specifically designed to have a certain width as it goes around. So it's quite narrow to start with, but the more that vane is moved round, the bigger the gap between the tip of the vane and the actual casing. It is calibrated. As that moves round, it moves this potentiometer, okay, this little valve here. Again, that will give a reading to an amplifier. Amplifier will give a reading to your gauge, and that will tell you how much fuel you're using as you're doing engine run. It's quite crucial because when you're flying long distance or at any point, you need to be able to check how much fuel you're using. On a bigger commercial aircraft, the flight engineer can calculate, have they got enough fuel to go to where they're going. They might be in a headwind, or likewise, it could be in a tailwind. We'll get even quicker and use less fuel. And it's all about cost as well. How can they save money as they're flying? But again, safety as well. If you've no fuel flow on engine run, could be a few things. Could be a faulty gauge. You might have no fuel. You might have run out of fuel. or you forgot to put the LP cock on, or there's a blockage. So there's lots and lots of things. So as you're doing ground runs and the pilot's flying, you're checking temperatures, RPM, speed, fuel flow, oil pressure, lots of things you're all checking at the same time. And if any of these fail, then unfortunately, yes, you will get an alarm or an indication in the cockpit as you see fit. But again, there's a few different types we'll look at as we move on. So basically the low pressure side. High pressure side, yes, we'll have the LP shutter valve to start with, so from the fuselage. That's usually behind a firewall of the actual aircraft before the engine. The engine will be in a separate compartment, engine bay. There'll be a physical wall, and the LP fuel valve is usually behind that firewall. Once your fuel valve is opened, then we can supply a fuel pump. That fuel pump will then deliver through a regulator, maybe through a governor as well, and to the pilot selection for HP cock. So the fuel will always be supplied to the high pressure shutter valve for the HP cock, and once a pilot or use an engineer open that, that will allow fuel to go to the burners. Okay, once you have rotation of the engine. All right, and then providing that's working okay, you can go flying or do your ground runs, etc. So that's a basic high pressure fuel system. All right. Okie doke. Not too far ahead. But again, we're going to look at how this operates, how we control. We don't just switch fuel on and give it to the burners and that's it. We've got to control under certain pressures, make sure it's arriving at the right time, make sure it's going to burners correctly, and for changes in temperature, pressure, and speed as well. We'll look at a few bits and pieces there. Okay. I think what we'll do is we shall, before we move on to the really technical stuff, we'll go for that's almost 10 past now. We'll just go for a break now and come back just after about 5:30. Well, my 10:30, whatever time it is for you guys. So come back in about 20 minutes or so, okay, before we move on to the main components, because it does go quite in depth after this part. So get the coffee in or get your teas in and get ready for the technical part. Okay, so see you in about 20 minutes, guys. All right. Thank you. Okay, folks, back on again. Let's get going again.
Yeah.
I remember got back. Are we back? Most people back, I think. Okay, let's move on a little bit. So we'll start with the high pressure fuel system. We'll move on to the components and how do we control the high pressure system as well. Right, so principle of engine control. We to obviously look after the fuel system, we can supply fuel system, we control it depending on what's happening as well. So initially, to get fuel pressure, we need a fuel pump. Now the basic pump will be a spur gear type pump. And what I mean by spur gear is the gears in the pump look like spurs of a cowboy. Okay, it's cowboy boots. Hence a spur gear. A basic pump. The faster it goes is due to the engine going faster on the gearbox, because the gearbox, the fuel pump is attached to the gearbox through the drive. And pressure is not from the pump. The pump supplies the flow. The pressure is restriction to flow. So that's all your fuel pipes, the components, all that sort of part. Okay. So the pump supplies the flow. You do get a bit of pressure within the pump purely because of the restriction of the casing. Okay, on the side there. But as you can see, that in this case, the fuel comes in from the bottom, gets spun around the outside, and then gets spun out towards the direction of the system and the burners, etc. The basic pump will have an overpressurizing valve because we don't want too much pressure in the system. So if it does overpressurize, this is a basic one. We'll get more involved in the next pump I'll show you. And it will, any excess pressure will go back to the inlet side and go back to the low pressure side. Okay, but that's just this is just a very, very basic spur gear type pump. Spur gears are okay for supplying fluid, whether it's fuel, oil, whatever, because we'll see that in oil system as well, when there's not much changes in speed. When we need a bit more specific control, we'll look at a different pump, and that's what I'm going to look at just shortly as well. So that's a typical spur gear pump. We're going to look at what's called a variable displacement pump, next one. The main fact is you've got to supply the flow. Now, I'll try and get a picture probably lunch. I meant to put one on last night. This is a cross-sectional view of a variable displacement type pump. Now, I've got an animation that will help maybe show what's going on as well. Usually I can show the students in the hangar and show actually a mechanical one. So what we've got inside, there's a lot of things going on here, so we'll take a bit of time this one, because it does take a bit of time to understand what's going on. Now the pump itself, the whole assembly is bolted to the gearbox. There'll be a drive shaft, okay, here, which spins the pump. Now the pump is spinning a cam plate or swash plate, something it's called, and attached to that cam plate and swash plate are these little pistons that are going round and round and round and round. Now the difference between a spur gear pump, which is going round, it doesn't change, is this cam plate actually moves backwards and forwards depending on the input from the pilot and the pressure within the system, and that's controlled by a servo piston. So this piston will move forwards and backwards, which will move this cam plate forwards and backwards, and what that does, that allows more fuel to be drawn in to allow more fuel to be drawn out, pushed back out, and until it gets to a point where it's stable, where it'll just stay in the middle direction. Now usually when the pump's switched off, this spring here will push it to, in this case, as we see in the diagram, fully inclined, the maximum displacement. In other words, it's ready to draw as much fuel as possible until the pressure when the high pressure system builds up enough to stabilize. And once it's stabilized, it will wait from an input from the pilot or yourself as an engineer. Now for this to happen, we need a lot of things to work at the correct time. We also need to control the amount of pressure from the pump itself. We need to control the flow. So there's a lot of parts we're looking at here. So the colours we've got blue is representing a servo fuel pressure. Now servo fuel pressure, it's just a tapping or small tapping of fuel from the actual high pressure system, the high pressure fuel that goes to your burners. The green represents the governor pressure, the pressure that's actually within the pump itself, because there is fuel surrounding it all as well, so there will be the pressure will build up the pump, and we've got to manage that as well as the normal high pressure system. The yellow represents the low pressure system, the supply of fuel which will come through from the HP cock and that sort of thing. So we've got the low pressure fuel coming in, it gets drawn in through these plungers, it gets spun round and pushed out through another plunger on a different side. Now it's the same plunger that draw them in, push them out, but they're split into half, as in the sides are split. It looks like a kidney shape, sort of C shape on one side. So one side's purely for drawing the fuel in, and one side's for pushing the fuel out. And as I said, depending on the position of the cam plate, depends how much fuel is drawn in and how much fuel is put out. So the further to this side, then the more fuel is drawn in. The further to this side, the less fuel in. Once it's in line, it's balanced, it's happy, just sitting there. As I say, the blue, the servo pressure, which is a sensing from the high pressure system. You can see the high pressure there. So the yellow fuel will come in, and then the red will push the fuel out to the burners. But there's a little tapping here, which depending on the pressure that's in here, will give a sensing pressure to the back of this servo piston, which will stay where it is if it's balanced, or will move forward if there's more pressure, or backwards, depending on the pressure in the high pressure system itself. And it also depends on location of the throttle and other components. Now, being this variable displacement pump, we mentioned we need to have some sort of control. And in the pump, we've got what's called a governor. All right, a governor is what is in charge of everything. You think of a prison, who's in charge of a prison? It's the governor. You know, all right, a bit of slang talk for the English people to go, all right, governor. The governor's always in charge. So we've got a mechanical governor on this type of pump down here. Now what it is, it's a pre-adjusted or preset valve. Okay, so there's a rod here with a spring. Now we can just see bottom here, we can actually tension the spring, now increase the tension spring or decrease the tension spring by adjusting this bolt. All right. Now that will put a predetermined value on the pressure of this little diaphragm. The diaphragm is just like a fabric, okay, where you'll have the LP fuel pressure one side and you'll have the pressure within the pump the other side, so that they're pushing against each other. Whichever one's the highest pressure wins. Now, if there's a problem within the pump where the green governor pressure is built up too much, it will push down on this diaphragm, which will push this valve up, which will then rock what's called a spill valve. Okay. Now, a spill valve is like a seesaw. It's just going back and forth like that, and a little pivot point there. The spill valve in this type is called a half ball valve. Okay, that's one type of spill. We're going to get two types of spill valve. This one is called a half ball, because you look here, it looks like half a ball. Okay. Now, you just see there's a very, very small gap. There's always a tiny little gap there. It's never fully closed, but it does open. There's always a tiny little gap. We'll come on to that in a minute. So if the pressure, the green pressure, builds up too much, it pushes this valve up the way. That will push down this side, which will rock the valve off the seat of this the servo side. Now, if it does that, that will drain away some of the servo pressure. But if the servo pressure decreases, then your pump output will also decrease. And this is the main thing you need to remember from anything on this, is if servo pressure decreases, your pump output to the burners will also decrease. And likewise, if servo pressure increases, your pump output also increases. It's the same for same. If you remember that, you won't go far wrong when it comes to the exam question. Okay. So you can see here, let's say, for example, servo pressure has increased. Okay. So in other words, this valve will be shut. Servo pressure increases. It's going to push the piston across, which is going to increase the angle of attack. Okay, I call it angle of attack, angle of the cam plate, which will draw more fuel in, which will pump more fuel out. Likewise, if servo pressure decreases, that means that the HP pressure is going to increase. Okay, that will push against the spring, which will now bring this cam plate back away, which will decrease output. Now, joining on up here is a few more bits and pieces we're going to look at, reference with temperature and pressure, altitude, forward speed as well. Okay, so quite a lot to take in. I've got an animation to show you what's going on shortly. Without seeing the pump itself, it's a lot of things going on. But the main thing is we've got a variable plate. A spur gear pump is okay, but if setting hydraulics, if you use a spur gear pump for one system, that's fine. But if you use a spur gear pump for lots of systems, it can't cope. It needs to be able to draw more oil in. And like a fuel system, the fuel system responds to the input from the pilot. What it is doing, that this moving backward and forward, is ensuring there's enough fuel at the right time, at the right command by the pilot or yourself as an engineer. Okay, so it's not overfueling and it's not underfueling, and it's all automatic, well, mechanically automatic. This is mechanically controlled. There's no computer controlling. It's all preset by spring pressure and high pressure and servo pressure and LP pressure, all mechanically controlled at the moment within the pump. There are other aspects we'll look at shortly, but that's the basic of a variable displacement pump. Again, these type of pumps are using hydraulics as well. Very, very similar. They have a couple of extra attachments, but the principle is still the same. Hydraulics will use the same principle. Okay. So is everybody happy with low pressure? Everybody happy with high pressure? And what's happening with servo pressure? Have a little look at it first. Any questions? We'll go through it a few times because it takes a bit of time to settle in. Anybody got any questions on that so far? Silence is good. Everybody okay, yeah? Anybody lost with that at the moment?
Lost.
Don't worry, I expect the very first time. Once we're going through it a few times and you see the animation, it will make sense. We'll go through the whole system and then we'll go back into it and we'll put it all together. Hopefully it will make sense. Basically, it's just a pump. It's providing the flow to the burners. But if you have like an old spur gear pump, the previous one, oops, that one, that supplies flow, that's fine, but it doesn't compensate for demands and flow. Okay, it's just a fixed flow and that's it. Although the gearbox can spin it, and that's just a very basic one. The chance of that one could either undersupply or oversupply fuel at the wrong time. This one compensates by manually adjusting for the requirements by the action of moving the throttle lever, or for climate, pressure and temperature. Okay, it all depends on the pressure within the system. When there is no input from the pilot or no response in the throttle, this will stabilize. If the aircraft's flying steady speed, no angle of attack, no increase in power, then this cam plate will move into pretty much the vertical position, the neutral position. Okay. As this is spinning round, we've got about maybe 6 or 8 of these little plungers. Okay. The cam plate is spinning. These little plungers, okay, I'll maybe try and call them next time, are rotating round. They're not stationary, just going back and forward. They're actually all spinning round. Okay, like that, all round. So as it goes round one point, in fact, what I'll try and do before I put animation on, try my worst drawing skills. Let's try and put this up. Let's see if this will work. Bear with me 2 seconds. The animation should help again, but I'll try and break it down into this. Let's make sure that's working. Have we got a pen? Yep, that's not there. Let's see if this works. Right, black screen there. Have we got a pen? There we go. Right. Let's go for the blue one side. Right. Going back to the diagram, these little pistons. Now, if you look square on, oops, who's that come in? This cam plate, which goes back and forward. Okay, if I put, let's see, that's right now before I start drawing. The cam plate at the moment. Okay. Right, there's a cam plate, and then you'll have pistons, all the same size. Okay, cylindrical pistons. Now these are rotating round and round. If I look square onto it, it's round, and these little pistons will be like that. Okay, looking at the end of them. And the pistons are just cylindrical, standard pistons, and what they've got is a little flexible end at the back of them. Excuse my bad drawing here. Okay, just stainless steel pistons with a little flexible end at the back. So that allows, when the cam plate moves back and forward, the ends move back and forward. Now these are rotating round and round and round. Okay. Now, on one side, where the pistons push the fuel in and out, is like a kidney shape. So we're looking like one side like that. Oh God, that's not so good. Probably making it more complicated than what I want. Now there will be holes, all right, on these kidney plates. The end of the cylinder, which should be here, okay, as that's rotating round, this kidney plate, which sits about here, is the output and input to the high pressure side and the low pressure side. So you can change the colour. So let's call, that's the high pressure side. Oops. So change colour again. And that there is, where is it? That's the low pressure side, okay? So as it's rotating, if you look at the end of it, you look square onto it now, as if we're doing here, looking at the front here, half the side in this case will be high pressure. So this, let's call this side the high pressure side, okay? And the other side will be the low pressure side. Oh, let's say again, my fault. It's not easy to draw on this thing. Okay. Come on. Yeah, it's not the easiest thing to draw. So as it's spinning round, these pistons, as they spin round, will either draw fuel in. Okay, as they're spinning round like this, one side they will draw fuel in from the LP side, And as they get pushed round, they will then push the fuel out to the high pressure side. Okay, so there might be 6, maybe 8 of these little cylinders rotating round, and you can imagine that as the cam plate moves backwards and forwards, it will increase how much it draws in and how much it pushes out. Where it's in line, it's just even, just going round and round and round. But as it's going to one side, the piston, as it goes round, will be shorter and longer. Okay, as it's spins. It'll probably easier to see in animation. I'm just trying to show a little bit there. Let's see. Right. So yeah, these little pistons. So where this part here is, this part here, that's split into 2 parts. It's not one complete part. It's split into 2 parts: LP side and high pressure side. So this sort of kidney type shape going in. Now, LP pressure is LP pressure. That's just going to be standard. But the more it draws in, then the less angle will be at the top. Okay. So as it's pushing the fuel out, that will increase the flow. It's pushing out quicker. Yeah. So if it increases the flow, that will increase the pressure within the system. In other words, make sure the pressure at the burners is correct for that positioning. But we need to control that. So the high pressure system here has a tapping which goes to a restricted gap there. Okay, that restricted gap there. Now that slows down, it will speed up the flow. It's a little sensing line which will also go to the back of this piston. So you've got the high pressure fuel trying to push the piston this way. You've got the spring in here trying to push the piston that way. All right. So can you imagine gets less, and that spring pressure will push that across and provide more fuel. Okay, it's need to the servo pressure has increased. Okay, now the only way servo pressure can increase is if your spill valve can look at. So if spill valve is closed, the servo pressure will increase. Well, if servo pressure increases, it's going to push this piston across. That's going to push this cam plate across, which will increase the pump output. Okay. If servo pressure decreases, well, that means the high pressure on this side is going to be more than the servo pressure. That will then push the piston across this way, which will decrease. So the main thing to remember is servo pressure increases, pump output increases. Servo pressure decreases, pump output also decreases. Okay. If the pressure from the pump gets too much, then the spill valve will open because the servo pressure in the green will push on this diaphragm. So the diaphragm, just like in the wedge in that supersonic intake, will move up. Okay, which will move this valve up the way. That will rotate this seesaw type valve, which will move it off there, the spill valve. The gap will become bigger, which allows servo pressure to go back into the low pressure side. So in other words, servo pressure will decrease, therefore pump output again will also decrease and then re-establish once it gets too much. Now the reason that might happen is the pilot might have brought his throttle from maximum to idle very quickly. What's going to happen there? You'll get a back pressure. So the back pressure gets felt within the pump. The pump reacts by the governor opening the bleed valve. The bleed valve, or the spill valve in this case, spills some pressure off the high pressure side, and that decreases the pump output until it stabilizes again. Okay. You can just see here's a little tiny filter as well, last chance filter for the pump. We don't want any debris going in the pump. Okay. So we'll get into the animation in a minute. I'll show you what's going on. Okay, so that's the basic, but we'll cover this a few times. It does take a little while to settle in. Okay, let's go back there. Right, this is animation. Hopefully this will work. You might not hear anything on this, unfortunately. So there's the basic pump. This is actually taken from a hydraulic pump. The only extra thing is got this part on the side, but the pump itself is a variable displacement one. So what they're going to do is going to strip it down, show you what's inside. Okay. I'll speak about some bits as we go along. Now there's the cam plate with the pistons. There's your drive, also for spinning the pump, bearings, the shaft and all that sort of good stuff, and the housing itself. There's your swash plate or cam plate. and the kidney side is this point here. All right. Now there's your servo piston at the bottom. And this is the flexible part that moves the cam plate back and forward. Okay, so it's moving the angle of this back and forward. And there's a kidney plate type shape I was on about. Okay, so depending on the angle of these pistons, okay, will determine how much fuel gets taken in to how much fuel gets pushed out. So the greater the angle, the greater the fuel. So let's see it working. So that's your servo piston there, which will go back and forward. So again, this will all be attached to the gearbox. So the gearbox will be spinning at the speed determined by the RPM of the engine. And then you can see this sort of kidney shape there. So one side is input, one side is output. So we'll see this operating just in a minute. Now the low pressure is in blue, the high pressure is in red. So you can see in this case it's sucking the oil in, or in this case it could be fuel. So these plungers are sucking the fuel in. As they come around the other side, they push we'll say it's fuel, they're pushing the fuel back out. Okay, so depending on the angle of the swash plate determines how much fuel comes in and out. So there's the sort of C shape I was trying to draw for you on each side. Yeah, so drawing the fuel in, pushing the fuel out. Draws the fuel in, and as it goes around the other side, it pushes it out on the other side. It's the same. You see these flexible ends at the side of the pistons? They allow the balls within there to move. There's your servo piston. So there's decreasing the angle, which decreases the output. This one's actually got a separate spring to the actual servo arm. There's the servo arm moving, okay, against spring pressure. So if pressure decreases in servo, the spring pressure will win. Okay. In this case, in the hydraulic pump one, it does the opposite. It actually works a different way to the fuel pump. This one actually draws more in. You can see the change here. The swash plate is moving. It's changing its angle. All right. And that's a basic variable displacement pump. This is a hydraulic one, but the principle is exactly the same as a fuel pump. Okay. Exactly the same. That should be up. All right. That's what we're looking at there. So there's your piston with a spring. The hydraulic one had a separate spring or a different one, so it actually worked back to front. All right. So in this case, that moves forward. That will draw more fuel in, push more fuel out. Okay. All there. And then for protection, as I say, we've got a governor. The governor's in charge of the pressure in the pump. Now we'll open the ball valve, which will allow servo pressure to decrease. Well, if servo pressure decreases, okay, that's going to decrease output. In other words, the high pressure here is going to decrease. Then eventually it will stabilize. Likewise, if servo pressure increases, then that will build up and push that rod, okay, across to bring more fuel in until the fuel stabilizes, and then it will balance out again. The high pressure will build up once again and push it back to a halfway position. Okay. So there's a close-up of the governor. Now, as I said before, there's a governor. So if the pressure builds up, it pushes up this little diaphragm, pushes the valve up. This spins, opens the spill valve, and releases pressure. Now, the reason it senses the pressure difference, we've got what's called centrifugal drilling. So the LP fuel, as it's coming round, gets thrown centrifugal force. These are calibrated drillings that will affect the pump casing pressure. As I said before, there's always a tiny little gap just between the bottom of the valve and the servo pressure line. Okay, it's never fully closed. It's just a tiny little gap. Now, things to watch out for is the governor pretty much works no problem 99% of the time, but just in case something goes wrong, let's say there's a bit of damage to the diaphragm, so there's a hole in the diaphragm. Well, what's going to happen now? Well, the governor isn't going to control. So if the governor doesn't control, there's a chance that the pump will just build up pressure, build up pressure, build up pressure, and just go bang, okay? and potentially the engine could explode as well. Too much fuel pressure going to the burner, too much fuel, bang. So as a precaution, because of this tiny little gap here on the valve, the centrifugal drilling pressure, the LP fuel can just about squeeze in here if that builds up high enough, and it will actually physically move the valve off its seat, again decreasing servo pressure. So again, if you decrease servo pressure, you decrease output. However, what could potentially happen is it will open and shut, and what you'll hear is the engine going sort of hunting, as we call it, and that's an indication the governor isn't working correctly. So there could be a bit of problem with the diaphragm. But initially, it will save the engine from getting too much fuel and potentially exploding, especially in the pump anyway. Indication in the cockpit is you'll lose pressure, power initially, a little bit of power, and then it might come back on again. So that's an indication that this rocker arm here is going back up and down, okay, because of the pressure of the centrifugal drilling. Okay, the pressure will get through here, move it up, and then it will stabilize, then it will build up again, it will close, it will open, it will close, it will open. So you get this hunting effect. But overall, most of the time it's working fine. You don't often get a problem with the diaphragm. Sometimes though, you might get the spring. The spring itself might break because it's opening and shutting all the time. So fatigue can set in. These are not on condition item. Sometimes they weaken, and you can actually adjust it by adjusting the turning the bolt in or out, which will increase the tension or decrease the tension. Again, all the corns with your manual. And there are ways of testing the governor that is working as well on the ground. Okay, so centrifugal drillings, just in case there's a damage to the diaphragm, spill valve will open, decrease servo pressure, decrease output. Okay, should not work. All right, so that's the overspeed governor. That's the diaphragm fail I was on about. So diaphragm fails, engine would run to maximum RPM and beyond. In other words, potentially blow up. We don't want that. So that's the fail safe that's built in. So that ball valve that I just showed you there, up here, okay, will lift and drain off some servo pressure. Now the first type of ball valve I mentioned is called the half ball valve. There's the pivot point. Okay, so it's just rocking up and down on a pivot. Your servo line, there's always a tiny little gap, as I said there, and that's why it's called a half ball valve, because it looks like half a ball. All right. So depending on how close that ball valve is to the servo line will increase pressure. The further away it is from the servo line, it will decrease the servo pressure. So just remember that increase servo pressure, increase output, decrease servo pressure, decrease output. I'll keep saying that. So that's your half ball valve. Then we've got another one called a kinetic knife valve. Now this valve does exactly the same thing as the half ball valve, but just in a different way. So if you look at the diagram here, we've got high pressure fuel in the sort of pinky red colour here, and we've got servo pressure fuel on the right hand side. Now in this position, the valve is in the open. We've got this knife, okay? Knife is in between the streams. So you've got high pressure stream one side, high pressure stream the other side, but the knife is cutting. But if you cut something with a knife, especially a hand, you bleed. So think as the kinetic knife valve, when it's in, it's cutting, it's bleeding. So the pump output is bleeding, the pump output therefore must be decreasing. So the kinetic knife valve is in, pump output is decreasing. In other words, the valve is open. Same as a spill valve, the ball valve. When it's open, it's decreasing. This is just a different method of doing the same job. Okay. You can see there, HP fuel is pushing against there, servo pump decreasing, so that means the swash plate, if I was to draw a line here, that means the line is now facing that way. The servo piston has brought the cam plate towards the spring. So in other words, the pump output is decreasing. Okay, no expense spared graphics. There's the closed position. So if you look at the bottom where the spring is, you see the valve, okay, is now going from open. So the servo rod is quite far that way, but when we close it, it's gone the opposite way. Now, if the valve is closed, the knife is out. Okay, so the knife, we're not bleeding pressure away, we're actually increasing pressure. So the valve is closed. Like the ball valve, as it came down on the servo line, that closes pressure, which increases pressure. The knife valve does the same thing. It basically closes because it is not interrupting with the flow. Okay, so the knife is out of the way. Servo pressure now increases because you've got a tapping from high pressure, increasing the servo pressure. Servo pressure pushes the piston across this side, which pushes the cam plate across, which draws more fuel in, which increases pressure. So again, pump output is increasing. Same as the half ball valve closing, same as the kinetic valve closing, your servo pressure increases, pump output increases. So go back to the previous one where it's open, we're bleeding. Valve is, the piston, servo piston is moved to the right, so it's decreasing, but when it's closed, it's moved to the left, which is increasing. Okay, again, it's just a different method of doing the same job, called a kinetic knife valve. So we've got open, closed, and then intermediate. Well, it's not quite in, it's not quite out. Okay, so it's sort of balanced. In other words, this time the cam plate will be vertical, it'll be stationary, it's waiting for an input. So we're pretty much balanced. We've got roughly half and half here. We're not bleeding too much, we're not fully closed, we're just at a stable condition. That's the intermediate. Pump output, in this case, is constant. Okay. Everybody be okay with that one? It's just a different way of, instead of using a half ball valve, we're using a kinetic knife valve. So if the knife is in, if you, as I said, if you cut yourself with a knife, you're bleeding. So think of this, the knife is in, the valve is open, it's bleeding fuel pressure. If the knife is out, well, there's no cut, so you're not bleeding. There's no open cut there. So not bleeding, that must be closed, so pressure is increasing. And when it's halfway in, it means it's a constant. Okay. So that was the pump and two versions of bleed valves. Okay. So depending on which bleed valve you're using, if the valve is open, we're bleeding, we're reducing pressure. So servo pressure is reduced, pump output is reduced. And likewise, when either valve is closed, we're increasing pressure. So we're increasing servo pressure, we're increasing pump output, pump delivery. Well, that's all very well with reference to speed and pressure. But now what we're going to do is look at changes in altitude and changes in forward speed of the aircraft. Okay. So what's going to happen with altitude? What's going to happen with altitude? If we go up and up and up, will it increase or decrease? Anybody? What will happen with altitude? Will it increase or decrease?
Once again, question please.
Yeah. What's going to happen when an aircraft goes to altitude? Will pressure increase or will pressure decrease? What's going to happen to air pressure at altitude?
Increases.
The higher we go in the sky, what happens to pressure?
Decreases.
Yeah, it decreases. Yeah, the air gets thinner, it decreases. So we have to account for that. We can't be putting the same amount of fuel in. If there's less air as we get higher and the aircraft's going at steady speed, we can't be putting more fuel in, so we can decrease the fuel as it goes up in altitude, depending on throttle setting. Now we don't want the pilot to have to think about that. He's too busy thinking about other things. What type of cup of tea he's going to get, what lunch he's going to have. All right, he needs to just open the throttle and the mechanical system will take over. So what we've got is a mechanical system. Now, the diagram we saw before, we saw the high pressure line, the servo line. So this is a continuation of the servo line, which will go to your servo piston, okay? We'll join all this up later on. So we've got the servo pressure. And again, look, we've got a spill valve. Remember what a spill valve does? It bleeds or closes or stays intermittent. So again, if we open a spill valve, it's going to reduce pressure, reduce output. And likewise, if we close the spill valve, it's also going to increase pressure, which increase output. So how is this going to work at altitude? Well, let's have a look. We've got this capsule here. which is called an evacuated capsule, also known as an anaeroid capsule. In other words, it is sealed at sea level conditions. So on the ground, this capsule would be made and it's fully sealed. There's no openings in it. It's got air inside it from sea level conditions. Okay? Don't worry about this one at the moment. So the top one here is evacuated. You've got LP fuel pressure in here, all right, just as a reference pressure. Now, if that's got sea level air inside the capsule, what's going to happen in that capsule as I go up into higher altitude? If that's got sea level pressure in it, will it expand or will it contract?
Contract.
What do you think? So we've got sea level air in here. Now it's sealed, it can't escape. Okay, so we've got sea level pressure. So let's call it 15 psi. I'm going to fly up to 20,000 feet. What's the pressure going back 20,000 feet compared to sea level? Is it going to be less or more?
It will be less.
Yeah, so the sea level, the pressure at 20,000 feet is going to be less than what the pressure is in that capsule, isn't it? Because we've got sea level pressure in this capsule. So what's going to happen to this capsule? Will it expand or contract?
Contract.
Ooh, 50-50. Some say expand, some say contract. Normally in the class I would say put your hand up for expand, put your hand up for contract. And I'll try and place a, see who thinks the best one. So who? Right, some people say contract, some people say expand. So have a think about it. We've got sea level pressure in here. Let's call it 15 psi. At 20,000 feet, it's going to be what? Oh God, it'll be about maybe 8 psi. Okay, so there's less pressure up there. So let's think again. Will that expand or will it contract?
Outside pressure is low, so I think that will expand.
Correct, it will expand. Have you ever flown an aircraft and you've maybe had some food on the aircraft and there's maybe a pack of crisps? Yeah. Now, a pack of crisps at sea level, it's quite, you know, flimsy. But if you take the same pack of crisps and you're in an aircraft, it expands. Yeah, because it's got sea level pressure in there. Although the pressurized cabin is trying to make sea level conditions, the sea level pressure crisp makes the crisp packet quite full, doesn't it? Okay. Well, this capsule, because it's got sea level pressure in it, when it goes higher, well, there's less pressure at the altitude, so the high pressure in here is going to win. So it's going to expand. It's going to get bigger. Now, as it gets bigger, it's going to move the spill valve. In this case, it's going to move the spill valve down the way. Well, if it moves the spill valve down the way, it's going to open the gap at the servo pressure. Well, if it opens the gap at servo pressure, that's spilling, it's bleeding the pressure away. So if it's bleeding the pressure away, that must be it's reducing pressure, so it's going to reduce the pump output, which makes sense because we don't want as much fuel at altitude because there's less air. Less air means less, we need less fuel to do the same job. Okay, so this expands, pushes the lever down, opens the gap at servo line. That will decrease servo pressure, which will decrease pump output again. So again, a spill valve doing its job. So this one here, the evacuated capsule, also known as anaeroid capsule, is for changes in altitude. Okay, and also changes in temperature, because temperature could affect that, couldn't it? Down below, you could have a very, very hot day. Okay, or if you're flying straight and level, you go from a hot environment to a cold environment. Hot environment, that's going to expand the air. Yeah. A cold environment is going to contract it. So if it's cold air is dense. Hot air is less dense air, less fuel. More dense air, more fuel. So if it gets a hot day, a hot altitude, that will expand. Less air, less fuel. It means it has to spin quicker. Colder air, cooler, it's also going to contract this, which will close the valve off, which means cold air, more fuel required. So we need to close the valve off. So anytime the valve closes, that means we're getting more pressure, more fuel. Anytime the valve opens, that means we need less fuel. But it's altitude due to pressure or temperature as well. Okay. So that top capsule accounts for pressure and also temperature conditions. And that will be affected by, obviously, you've got the fuel pressure, the LP fuel pressure in there, which, so obviously when it spills off from the server pressure, that'll go back in the LP side, and that'll go back to the pump and so on and so on. Okay, so that was the top one. That was the evacuate capsule. All right. Now the bottom one is also a capsule, but this time it's not sealed. It has an opening. It has an opening to intake air pressure. Now that would be, I wonder if I can draw some of this. Let's see if we can get this to work. It might work, it might not. Right, so I'll put up here ambient, so that will be P0, yeah? So this one here, intake air pressure, what annotation would that one be, do you think?
P1?
P1, yeah. So we've got a comparison going on. We've got a comparison between P1 and P0. P0 is your ambient pressure, temperature, which this one will sense. And this one here has got open line to P1. Now, what do you think is going to affect pressure at P1? If that's intake air pressure, what could make this, let's change that there, sorry. What do you think could make this capsule expand or contract?
Forward speed.
Brilliant, yeah, forward speed. The faster that aircraft's going, so there's your intake, but the faster that's going, the more ram effect, the more air we're ramming into that intake, yeah? So if that's going really fast, we're going to get lots of pressure. Well, if we get lots of pressure going into this capsule, what's going to happen? It's going to expand or contract.
More air.
Contract.
Expand.
Yeah. Which one? There's two there. Think of
It
this.
will expand with more air, right?
Yeah. Think of this as a balloon. Yeah. If I put more in a balloon, what happens to the balloon? It expands. Okay. So if you've got fast-moving aircraft, that means more air getting pushed into here, which means it's going to go up. Yeah, it's going to expand. So if that expands, well, this time it's going to move the bleed valve up the way. Well, if it moves the bleed valve up the way, it's going to close off the bleed valve. So if it closes off the bleed valve, that's going to increase servo pressure. So therefore, if we increase servo pressure, we increase pump output. Because if you've got more air, that means we need more fuel. Yeah? So by shutting the spill valve off, we increase servo pressure. That moves the servo piston across to move the cam plate to induce more fuel, to suck more fuel in, to push more fuel out. So in other words, more air, more fuel. And likewise, if that contracts, when there's less pressure, maybe because of ambient pressure out here, okay, it expanded, that's pushing against it, well then we'll have less air, this will contract, and likewise, that will open, okay, and decrease servo pressure, which decreases pump output, okay? How's the brains at the moment? How's the heads? Bit more in depth now, isn't it? Okay, so basically P0 and P1. Okay. So what I'll do, I'll let that soak in your brains for the moment. We'll go for a break. What time? Oh, it's a bit later now. Yeah, come back in about 20 minutes or so. 25 minutes. We'll come back for about 11:45 my time, which is sense. All right. So, on to the next part. We'll recap that. Now, the pilot obviously has an input from you. You've got LP cock, you've got HP cock and the throttle. So the HP cock is just the on-off. You can see there, which allows the fuel on or off to the burners, and depending on what's happening with the speed of the pump at the time. LP fuel is always available, etc. Okay, so that's just the pilot's input. He's just an on-off valve for the HP cock. Then you've got the basic throttle. Okay, now this is just a basic throttle. We've got a gear here, that when the pilot obviously moves the lever forward and backwards, like a rack and pinion on your car for your steering wheel, that will move this little valve backwards and forwards, which will increase the hole or decrease the hole accordingly. That's just a basic, basically like a flow valve, to be honest. Sliding throttle valve, it's just a basic one. It's not very efficient, as in it could potentially overfuel or underfuel at the wrong time. So we need something that's going to help it a bit better. But basically, if I had to move that valve back, that opens the hole there, okay, and there's more fuel to the burners. And likewise, if I close it, it reduces. It's just a flow control valve. That's basically what a throttle is, a basic slider throttle. And that could be something similar like to that in a motorbike. Okay. Again, you can adjust reference pressure as well. That's a basic one. The other one we're going to look at is what's called a dashpot throttle. Basically a valve within a valve. Now, I've tried to colour it, the bits in your book. I think you've got the same ones in your old books anyway. But what I've tried to do is animate it a little bit. It's quite hard to animate, unfortunately. But if you go back to this one, you've got the one valve here. It just goes backwards and forwards, okay? So remember that for the moment. And then think of this one, this white part here, with this valve, as that previous one. The bit that goes forwards and backwards. Now, rather than just have one valve going forwards and backwards, we, depending on the pressure in the system, can affect if we have too much fuel or not enough fuel. So what we do is we have a valve within a valve, if that makes sense. So we've got two free sliding valves, okay? So we've got the inner one, which is attached to the throttle lever. Then this blue part, okay, which is a valve that surrounds the other valve, okay? And that's your throttle valve. So the control valve is the pilot input. The throttle valve is one that's outside the main valve, which will move accordingly to pressure in the system. Now at the moment, we've got the dashpot throttle in what's called the closed position. So as you can see there, there's your pump delivery in red as usual. So there's a little gap, there's not much there, it's in the closed position, so there's not really much fuel going out at all. Yellow, still the LP fuel pressure for reference. Then you've got your throttle servo, okay, which is this little part here. So just a little sensing from your high pressure side. That's all throttle servo, it's just a sensing pressure. And then you've got a throttle control, which is like a dampening fluid. So the fluid that's in there is a dampening. Now, the main valve, okay, your control valve and your throttle valve are linked by a spring, all right? So the spring's there to act as a, I class this like a shock absorber. Again, go back to my car analogy and motorbike analogy. If anybody worked on cars and motorbikes, changed the suspension at all? Have you removed springs or shock absorbers of your cars and motorbikes? Anybody done? Yeah, anybody did? Yeah. Well, inside, if you've got a shock absorber and a spring, well, think of this valve as a shock absorber and your outside valve and your spring as a spring outside of it. Inside the shock absorber, you might have gas or fluid to act as a damping fluid. Well, this would be this part here, okay? So initially, we can move the throttle lever forward, which will bring this control valve that way, which will try and increase the hole. Now, normally, that would open up a hole for the fuel to go to burners. But that could be too quick initially, especially if the pilot goes bang like that, moves the throttle really quickly. So with this sensing fluid there, okay, that spring is going to try and stretch and try and pull this valve, the throttle valve. But because you've got the sensing pressure in here, the spring will, depending what's happening with the pressure in the system, will control how fast this outside one moves in conjunction with the main control valve. So control valve, the pilot will move, and then the outside one will move with it, depending on the pressure in the system. It will either move at the same time, or it will move slightly after, okay? And it works as a dampen. It dampens out the pulsations in the fuel delivery. So how does this all work? Well, a valve within a valve, in the closed position, so there's not much of a gap. Now, not my best animation, but if you look at the next one, okay, you can just see, if you go back to the closed one, there's no gap there. The throttle valve is pretty much stuck against the housing, okay? If you look at the next slide, it is now opened up a little bit, okay? You can just see the gap there. Throttle valve has now opened up a little bit. So your servo pressure has increased because we've opened the main control valve, which will have caused servo pressure to increase initially, which will increase pump output. Well, if pump output increased, that means servo pressure has increased. So now this blue throttle valve is now trying to catch up with the main control valve. All right. The throttle control, that fluid just works as a dampening fluid, so it doesn't, come too quickly. The control valve will move, and then the throttle valve will catch up with it, depending how much pressure is in the servo pressure line. Okay, that depends how quick that moves. If you move the throttle very slowly up to maximum, then pretty much both those valves should, in theory, move pretty much at the same time. But if you put a rapid throttle movement, the control valve will open saying, yes, I need more fuel. The dashpot will move accordingly to the pressure that was in it. It's basically a smoother operation of controlling how much fuel comes out towards the burner. Okay, there's your HP output there. And so that's initial acceleration, and then if you look at the gap again, we're now at final acceleration. So the lever's now into full maximum position. You can see the gap here has now increased fully. The throttle valve is now catching up with the control valve. Servo pressure is increasing, and eventually it will stabilize. So both sides of here will stabilize, and it will sit pretty much ready for the next input or output. So that's a dashpot throttle. A very quick sort of basic explanation. It's just a smoother operating flow control valve. What does a flow control valve do? Controls the flow. A throttle is effectively a flow control valve. With a dashpot throttle, it is a valve within a valve that smoothens out delivery. It won't overfuel, and likewise, it won't underfuel. So again, if you slam the throttle back, okay, by decreasing, you'll get a back pressure, which will open the spill valve. That will drain the servo pressure off and allow this throttle valve to move backwards because of the throttle control fluid in there as well. Okay, so with a nice smooth operation, in theory, it should move pretty much the same. But if you move a rapid throttle, then the control valve or throttle valve will catch up with it eventually. I say eventually, it's all quite quick. It's like a shock absorber in a car. If you take a shock absorber out of a car and just use the spring, what's your suspension going to be like? Very, very bouncy, isn't it? It's going to be quite bouncy. The shock absorber dampens, so you get a nice smooth bounce in your car. Well, this is pretty much the same effect with a throttle. Okay, the dampening fluid is your shock absorber, your spring is your spring, and you've got one moving within another. So the initial one would be your shock absorber, and this one would be your spring on the outside. Telescopic forks and motorbikes, you've got the same thing. You've got a spring in there. You've also got dampening fluid. If you take the dampening fluid out of your shock absorber on your telescopic forks and push bike or a motorbike, it's very bouncy. Yeah, you put the right fluid in there, the right amount of fluid, and it dampens it out. So when it goes down, then it comes back nice and smooth. Well, this, as I say, is same sort of principle for a dashpot throttle. Older cars use a dashpot throttle as well. Some of the old carburetor cars, they have engine oil as the fluid. Okay, so when you lift the throttle up, and then it slides down slowly. So it's not a rapid up and down movement of the throttle valve. Because that, again, in cars and motorbikes that have that sort of system, will have too much fuel or not enough fuel at the right time. Okay, so that's a basic principle of a dashpot throttle. It's an older system now compared to what is an aircraft. Against all electron controlled, this is all mechanically controlled. Okay, so a dashpot throttle. So a valve within inside a valve. All right, so your control valve, come back to the original one. So your sliding valve here would be your control valve, this one here, your throttle lever there, so it's just on and off, so opening or increasing the gap. So there it is there again, this white part here. All right, that's your control valve. And then the actual throttle valve will determine how much that moves depending on the pressure from your servo line. Okay, so that also goes back to what we spoke about before break, your spill valves. If the spill valves are closed, servo pressure is increasing. So if servo pressure is increasing, then servo pressure here will increase, and that will push the throttle valve closer to control valve, depending on the pressure in the system. Okay, so there it is, opening, and then final acceleration. And as you can see there, there's the final gap for the burners. So the fuel is now more accessible. It's all calibrated. You've got holes in here, calibrated holes as proportional to the position of the throttle valve. which will be proportional to the burners. Okay, so that's a basic principle of a dashpot throttle. And final, not a final bit, but certainly one of the main bits we'll look at for, I'll say there, yeah, the two more bits to look at before we finish for lunch is we spoke about before the break the vacuum capsule and your open capsule. So vacuum capsule also known as aneroid, so that was P0, and this one here was P1. So for altitude and temperature, and for forward speed or ram ratio, okay, ram pressure. Now that moved, these two moved the spill valve. We've also got another connection to the spill valve. So there's lots of things that are controlling the servo pressure output and input. So let's have a look. If we've got another diaphragm here, and it's got a spring. Now normally the spring here will be trying to push that valve up to keep pressure increased. Okay. Now upstream of throttle, well, this red line is your high pressure line. Okay. So if we open the throttle, what's going to happen to the pressure here initially before anything happens with the pump? If we open the throttle, will we get an increase in pressure or a decrease in pressure initially before anything happens? What do you think is going to happen? So if this is connected to your throttle, it could be a dashpot throttle, it could be a normal control valve. If it's normally closed and we open it, if we open something, what happens to pressure?
Decrease in pressure.
Yeah, it decreases. We open something, we're going to let something out. So if we let something out, initially what's going to happen is the high pressure line here will lose a bit of pressure. So this spring underneath here will push up because it's going to win. It will then close the spill valve. Servo pressure is now going to build up, so servo pressure is going to increase, which means pump output is going to increase. And as pump output increases, delivery increases, which means upstream pressure will also start to increase and then balance out once the pressure has equalized. So the pilot or yourself as an engineer has demanded more fuel. Well, the pressure drop control diaphragm sensed that by a drop in pressure of the upstream throttle, okay, before we get the pressure from the pump. So the spring takes over, pushes the spill valve up to close servo pressure. Servo pressure is closed, so servo pressure has nowhere to go, so it builds up pressure. In that words, it's going to move back to your servo piston, move your swash plate, move to more input for fuel, which will give more fuel output, which will then increase your HP delivery. HP delivery increases, re-establishes the pressure in there, and then your spill valve will settle down to whichever position. Okay, so until the next input or output from the throttle. So that would be on an open throttle. So let's look at the opposite way. Let's see what would happen if you close the throttle rapidly. Now we're upstream of the throttle, yeah? So if we close the throttle and we've got flow going, what's going to happen to pressure now? Will it increase or decrease? What do you think? So we've got a fast running engine. We bring the throttle back to idle quite quickly. So initially, what's going to happen before anything happens to the pump? Will the upstream pressure increase or decrease?
Increase.
Yeah, it's going to increase. It's got nowhere to go. So initially, it's going to increase. Now, all this happens very, 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 very quickly. Yeah, everything's all blink of an eye, all very quickly. But in slow time, upstream pressure, think of a river. You've got upstream, you've got downstream. So in a river, if you block off a river, well, that water's got nowhere to go, so it's going to build up pressure. So same with the fuel. The fuel has nowhere to go because we've shut the throttle valve off. So the upstream pressure will build up. So now this time, the upstream pressure will be more than the spring pressure here. So that will push the valve down the way, yeah, against that diaphragm. Well, if that goes down the way, it's going to open the spill valve. Well, if the spill valve opens, that's going to bleed off servo pressure. If servo pressure decreases, then the piston goes back the way, servo pressure decreases, pump output decreases. Until again, the pressure stabilizes in the system, waiting for another command from the throttle. Okay, so that is your pressure drop control diaphragm. It's sensing what's happening upstream pressure with reference to the throttle position. Okay, So now you've got 1, 2, 3 things all in this controlling the bleed valve for servo pressure, as well as the pump controlling output from the governor with the pressure in the pump. So you've got 2 spill valves, one for pressure, altitude and temperature, one for ram pressure, and one for a pressure drop control with the throttle, all fighting against each other. Whichever one is the strongest is going to win. Okay, but it's flying at altitude, diving, going faster, throttle input, increase or decrease, or with the pressure within the pump itself, all acting together until it settles down. Okay, so that's your pressure drop control one. All that part there. Okay. And so we continue to this one. We can also add an electronic function. Again, automatic. Now, this one, we've covered this part, but we've also got an electrically operated version. Instead of mechanical pressure, we've got a solenoid, electrical solenoid here. Now, only time that will activate is when we get an overspeed from the LP spool. Now, if the LP spool, your N1, your LP spool, your low pressure spool is going too fast, well, if that's going too fast, that means the high pressure spool is going too fast. And if that's going too fast, that means we could potentially overstress the engine. We've got too much fuel going in. So we need to reduce the fuel. We need to spill some fuel off. So if we get a signal from the LP spool speed sensor, it will energize this solenoid like a magnet. Okay, it will then open a spill valve here, just the same as it does here, but this time it's got its own spill valve. It could be a half ball valve, could be kinetic, depends what type. And again, that will spill pressure. The servo pressure here will build up enough to open the spill valve here, which will bleed off servo pressure. So servo pressure reduces, pump output reduces because it's going too fast. And it's also got a signal from the gas temperature control. So your EGT sensor, maybe in P6 or 7 or possibly 8, okay, depending on which type of engine it is. So if it gets an overspeed signal or it gets a hot signal from your EGT gauge and reaches a predetermined temperature, it will also activate the spill valve, okay? So you get the throttle sensing pressure, puts more pressure on the LP side, that gets in between the spill valve opens again, bleeds off servo pressure, which bleeds off pump output. So now you've got all this and this all controlling that one poor little spill valve on its own. So these are all working together. So altitude, temperature, pressure, ram ratio pressure, throttle pressure, and speed and engine temperature pressure, all controlling this poor little valve. So this poor little valve is working quite hard. All right. So that's your other controls from there. Put it all together, and that's what you have. Okay, so we spoke about this is a slightly different version of pump, variable displacement pump. Okay, there's your vacuum capsule, your P0, your P1, your throttle, differential pressure control, your electronic control from speed, your temperature sensor. There's your dashboard throttle. Okay, there's your HP cock, LP cock, and your burners. You start. You might have a starter nozzle initially, and then you have your main. So your primary feed, and then your main feed. Okay, so it could be a duplex type system. All right. Depending on the upstream pressure, will determine what's happening here and what's happening here. Yeah, we open the throttle, we decrease the pressure. All right. So we decrease the pressure from up here. That wins. That pressure wins, goes higher, shuts off the servo, increases pressure. We've asked for more fuel. There's a little restrictor in here because the restrictor acts as a reference point where we don't want this to open too quick, too soon. So this is a calibrated restrictor. So again, the pressure will be here, it'll be going slower. The flow will be slower than it is here. This will be going faster, so it'll be reduced pressure. It's a more sensitive pressure. All right. But now you can see with other restrictors available, we put all this together, we can see we've got a governor, which is controlling the pressure from the pump. If it gets too much, it opens a valve. If it opens a servo valve, it decreases output. And then you've got your vacuum capsule and your ram ratio capsule, your throttle pressure differential, again, all opening the main spill valve, but it's a half ball valve or a kinetic knife valve. And again, same here, you've got the electronic control for overspeed and over temperature. And then as long as that's all working normally, it's down to yourself or the pilot to select the fuel using dashboard throttle, using a more sensitive version than a normal flow control valve. Okay. And there's your sensing pressure behind there as well. All going back and eventually all going to your burners. So I can't see you, but I was going to say hands up if you sort of half understand all that. Is anybody totally lost at the moment? Because we're going to recap this after lunch anyway, don't worry. I see a hand up there. Hands up, all good? Or all bad? Good, see the hands coming up. Is that a good sign or a bad sign? Would you be able to both? So you
It's
half
on
and half.
ideal position.
What's that?
Ideal position.
Ideal position. So could you talk through that whole diagram? Would you be able to, if I said to you, if I moved that throttle, what would happen here? When I got taught in the Air Force, we would get big diagrams like this, and an instructor would say, okay, I'm going to move the throttle to idle. Tell me what's going to happen. And we go, oh, we'd have to go explain what happened. And they'd give scenarios. So what we did initially, we broke down the pump, we broke down the controls. There's mechanical or electrical, and then the throttle, and then now we can put it all together, and that is a basic mechanically controlled fuel system, pressure control fuel system. Okay. So how are we feeling? Not too bad? Too bad.
Very
Well,
complicated, sir.
It is quite. It take a bit of time. Don't. It's easier in a classroom because I can draw on the board. I can do little bits here and there. It's a bit harder just online, unfortunately. But we'll recap this after lunch. Okay, we'll go through it a few times until we're all settled in. The main thing to remember from it all is if servo pressure increases, pump delivery also increases. If servo pressure decreases, pump output also decreases. As long as you remember that, you won't go too wrong exam. All right. But if you do if you understand what's happening with the valves, the spill valves, what properly the spill valve does, okay, that'll hopefully relate to it. It does take a little bit of time to go in. Don't worry. All the classes are the same. All right. After that, we'll move on to engine controls. So that, I think, is a good point to go and get some food, re-energize, okay, and have a drink of something. Okay, and we'll come back and we'll recap this one after lunch before we move on to controls. All right, because that's quite a lot to take in for the moment. So we'll go through it a few times, make sure we're happy, and then come back after some food. Okay, so we'll go and open our throttles, get some food down our necks, and get ready for afternoon session. All right, so again, see you back in just about an hour's time.